A distant world appears to break the universe's ultimate law. This is the story of a planet captured in NAS, a files that seems to move faster than light, a discovery that challenges the very foundations of physics. By the end of this journey, you will understand how scientists grapple with cosmic anomalies that defy explanation. We will explore the tantalizing data that suggested the impossible and the leading theory that turns this marvel into a cosmic illusion. How do you think we should react when the universe presents us with a mystery that seems to break its own rules? Every law of physics points to one unbreakable rule. The speed of light is the universe's ultimate speed limit. This constant, represented by the letter c, is not just a suggestion. It is a fundamental pillar of reality itself, woven into the very fabric of space and time by Albert Einstein's theory of relativity. This theory tells us that nothing in the cosmos, no particle, no spaceship, and certainly no planet, can ever accelerate to reach or exceed this incredible velocity. But why is this barrier so absolute? Think of it like trying to push a car that is rapidly gaining weight. As any object with mass moves faster and faster, the energy required to accelerate it further increases dramatically. The closer it gets to the speed of light, the more energy it demands, with that energy requirement soaring towards infinity. You would need an infinite amount of power to push something with mass all the way to light speed, a feat that is simply impossible. This is the ironclad law that every observation has until now obeyed. So when data emerges suggesting a planet has shattered this cosmic rule, it does not just present a puzzle. It threatens to unravel our entire understanding of the universe. The first hint arrived not with a bang, but as a subtle, almost imperceptible dip in starlight. Astronomers sifting through the relentless river of data from the Kepler Space Telescope spotted it, a telltale dimming of a distant sun. This was the classic signature of a transiting exoplanet, a world passing in front of its star and briefly blocking a fraction of its light. The initial reaction was one of routine excitement, another world to add to the growing catalogue. But as they calculated the planet's orbit, that routine feeling evaporated into disbelief. The numbers refused to make sense. To complete its orbit in the incredibly short time suggested by the data, this planet would have to be moving at a staggering velocity, a speed that the equations coldly stated was a significant fraction of the speed of light. In some of the more extreme preliminary calculations, it even appeared to breach that ultimate barrier. This was not just a fast-moving world, it was an impossible one. The initial shockwaves through the research team were not of celebration, but of profound confusion. How could a planet, an object of substantial mass, be dancing so close to the edge of reality itself? The data seemed to be screaming that the universe's most fundamental rule was being broken right before their eyes. The cosmic rule breaker has a name, and it orbits a dead star known as PSR B1257+12. This is no ordinary sun. It is a pulsar, the rapidly spinning corpse of a massive star that died in a supernova explosion. A pulsar is a neutron star, an object so incredibly dense that a single teaspoon of its material would weigh billions of tons on Earth. As it spins, it beams radiation from its magnetic poles like a cosmic lighthouse. If that beam sweeps across Earth, we detect it as a pulse of radio waves, an impossibly regular tick-tock that can be more precise than any atomic clock. This particular pulsar system is legendary in astronomy, celebrated for hosting the very first planets ever discovered outside our solar system. But within this family of pioneering worlds, one member stood out as deeply peculiar. The data pointed to a planet with an orbit so tight, so blisteringly fast, that its velocity seemed to flirt with the impossible. To complete a full journey around its star in the proposed time frame, this world would need to be moving at a significant fraction of light speed, a velocity that defied all conventional models for planetary motion. Here, in a system already famous for its discoveries, was the heart of our enigma, a world whose apparent speed threatened to rewrite the laws of physics. How could a planet survive in such an extreme environment, let alone move at a pace that seemed to break the universe's ultimate law faced with data that seemed to defy physics? The scientist's first instinct was not to celebrate a revolution, but to search for a mistake. This is the fundamental principle of science, a built-in skepticism that acts as a shield against our own excitement. An extraordinary claim requires extraordinary evidence, and a faster-than-light planet is perhaps the most extraordinary claim imaginable. The immediate question was not what this planet was, but where their calculations had gone wrong. Could the mass of the pulsar itself be misjudged? The orbital speed of a planet is dictated by the gravitational pull of its star, a pull that depends entirely on the star's mass. If they had overestimated the pulsar's weight, they would have also overestimated the speed needed for the planet to maintain its tight orbit. A simple error in this one foundational number could resolve the entire paradox. Another possibility lay in the planet's angle of travel. Our view from Earth is fixed, and we only see a two-dimensional projection of a three-dimensional orbit. If the planet's path is tilted in a way we cannot directly measure, our interpretation of its speed from the transit data could be completely skewed. What looks like a head-on, lightning-fast pass in front of the star might actually be a slower, grazing trajectory, creating a similar-looking dip in starlight without requiring impossible velocities. And then there is the chaos of the system itself. This is not a simple star with one planet. It is a complex gravitational dance involving multiple worlds and a stellar corpse. Could the subtle, cumulative tugs from other, unseen bodies be subtly altering the orbit of this one planet, creating an illusion of unnatural speed in the data? The scientific community began picking apart the evidence layer by layer because the universe is rarely wrong, but our instruments and our interpretations often are. The leading explanation for this cosmic paradox involves one of Einstein's most astonishing predictions, a phenomenon that acts as nature's own special effects generator. This is the concept of gravitational lensing. Imagine the fabric of spacetime not as an empty void, but as a vast, taut rubber sheet. When you place a heavy object like a bowling ball onto that sheet, it creates a deep dimple. Now, if you roll a marble nearby, its straight path will curve as it travels through this warped region. In our universe, mass warps spacetime in exactly this way. Stars, galaxies, and especially dense objects like black holes create profound gravitational wells, and just like the marble, light itself must follow these curves. When light from a distant object like our pulsar system travels toward Earth and passes near a massive foreground object, its path is bent. From our vantage point, this warping of light acts like a lens, distorting and magnifying the background image. This cosmic lens does not just bend the light, it can also create a powerful illusion of motion. If the alignment between the pulsar, this intervening lens, and our telescopes is just right, the lensing effect could dramatically alter our perception of the planet's velocity. The light we see is not taking a straight path, it is being funneled and stretched along a curved trajectory. This distortion could make the planet's normal, albeit incredibly fast, orbital speed appear to our instruments as if it has been amplified to a superluminal, faster-than-light pace. It is a cosmic mirage, a trick of gravity on the grandest scale, where the very medium through which light travels is twisted, making the impossible seem not only possible but measured and real. To unravel this celestial sleight of hand, researchers turned to the digital realm, constructing virtual universes inside powerful supercomputers. These sophisticated simulations were their laboratory, where they could test the gravitational lensing hypothesis against the baffling real-world data. They began by feeding the models with a range of plausible scenarios, starting with the planet's true, slower orbit. Then they introduced a hypothetical foreground object, a massive galaxy or dark matter clump whose gravity would warp the incoming light. The key variables were the mass of this lensing object and the precise geometric alignment between it, the Pulsar system, and Earth. They ran the simulations thousands of times, tweaking these parameters with each iteration, watching to see if this virtual cosmic lens could stretch and magnify the planet's apparent motion to the point of illusion. The results were a revelation. The models demonstrated that with a very specific and admittedly rare configuration, the observed data could be perfectly recreated. The phantom velocity, the signature of a faster-than-light object, emerged on their screens not as a physical reality, but as a ghost in the machine, a precise artifact of distorted spacetime. This turned a universe-breaking impossibility into a breathtaking cosmic coincidence, a perfect alignment that tricks our instruments and challenges our assumptions. It proves that sometimes the greatest mysteries are not in the stars themselves, but in the twisted paths their light must travel to reach us. Yet the allure of a truly faster-than-light object pushes us to consider ideas that border on science fiction. Beyond the elegant solution of gravitational lensing, there exist more radical theories that attempt to bend the rules of physics rather than explain them away. One of the most compelling is the Alcubierre drive, a theoretical concept born from the equations of Einstein's own general relativity. Imagine a spacecraft that does not move through space, but instead manipulates the fabric of spacetime itself. The Alcubierre drive proposes a method where space in front of the vessel is massively contracted, while the space behind it is dramatically expanded. In this bubble of warped reality, the ship itself would remain stationary, coasting along on a wave of distorted spacetime. Since the ship isn't accelerating through local space, the universal speed limit would not technically be broken. The space around the bubble, however, could move faster than light. It is a cosmic loophole, a way to cheat the ultimate law without ever technically breaking it. But is such a thing even possible? The catch is monumental. This theoretical engine requires a form of exotic matter with negative energy density, a substance that has never been observed and may not even exist in our universe. Could the strange planet around the pulsar be a natural example of such a phenomenon? While it is an incredibly remote possibility, it connects our cosmic mystery to a deep and enduring human fascination, the dream of breaking the light barrier and truly traveling among the stars. This planet's story serves as a springboard for that profound question: what if the universe has hidden shortcuts we are only just beginning to dream of? This particular case of the seemingly impossible planet is far from an isolated incident in the annals of astronomy. It finds a home within a fascinating and often misunderstood collection, NASA Unexplained files. These are not archives of secret alien encounters or hidden magic, but rather a formal record of observations that defy immediate explanation. They represent the raw edges of our knowledge, the data points that stubbornly refuse to fit into our existing models of the universe. When NASA scientists encounter such an anomaly, their response is not to proclaim a revolution, but to initiate a meticulous process of investigation. The data is questioned, the instruments are checked and rechecked, and every conceivable source of error is ruthlessly eliminated. This is the rigorous, often unglamorous engine of the scientific method. The goal is not to prove the impossible, but to understand the possible. A signal that looks like an alien transmission is more likely a passing satellite. A flicker that suggests a new physics is often a known instrumental artifact. But sometimes, after all that scrutiny, the mystery remains, and it is these resilient puzzles that become the most valuable treasures. The case of the faster-than-light planet is a perfect example of this process in action. It forced astrophysicists to confront their most fundamental assumptions. Did they truly understand orbital mechanics around a pulsar? Were their models of gravitational lensing complete? This single, baffling data point became a catalyst pushing researchers to question, refine, and ultimately deepen their comprehension of cosmic laws. It demonstrates that the greatest driver of scientific progress is not the confirmation of what we already know, but the persistent, nagging presence of what we do not. When the first whispers of this discovery reached the public, they ignited a media firestorm. Scientific journals cautiously outlined the anomaly with dense paragraphs of data and careful disclaimers. But newspaper headlines and online articles screamed a very different story. NASA discovers planet that breaks light speed. The nuance was lost in translation, replaced by the irresistible allure of the impossible. This chasm between the laboratory and the living room is a tale as old as modern science. The public, steeped in decades of science fiction from Star Trek's warp drives to the hyperdrives of Star Wars, was already primed for this revelation. Pop culture had done the groundwork, making faster-than-light travel feel not just possible but inevitable. So when a headline suggested science had finally caught up to fiction, it felt like a promise being kept, not a paradox being investigated. This created a dangerous but understandable gap. Scientists were grappling with a complex optical illusion, while much of the world was celebrating the end of physics as we know it. It is a reminder of how the stories we tell about the universe can shape our expectations, sometimes leading us to see revolution where there is only a reflection. History is filled with moments where the cosmos seemed to break its own rules. Long before this pulsar planet challenged our grasp of light speed, another celestial body defied explanation right here in our own solar system. The planet Mercury, the swift messenger of the gods, held a tiny but persistent secret in its dance around the sun. For centuries, astronomers meticulously charted its orbit, and they found a small, unaccountable wobble. The point of its closest approach to the sun, called its perihelion, was slowly shifting over time in a way that Isaac Newton's flawless laws of gravity could not explain. It was a minuscule anomaly, a ghost in the celestial machinery, but it was undeniably real. For decades, this was the unsolved puzzle of astronomy, a quiet reminder that our understanding of the universe was incomplete. Then came a young patent clerk named Albert Einstein. His theory of general relativity did not merely tweak Newton's laws, it completely reimagined gravity itself. He proposed that gravity is not a mysterious force acting across space, but the result of mass warping the very fabric of space and time. When physicists applied this new framework to Mercury's orbit, the inexplicable wobble vanished from the realm of mystery and became a precise, predictable consequence of the sun's mass curving the spacetime around it. The anomaly was not an error, it was a clue, a fingerprint of a deeper, more beautiful reality. This is the profound lesson that echoes from Mercury to our pulsar planet. A cosmic anomaly is not a wall that stops scientific progress, it is a door. It is the universe's way of whispering that there is more to learn, that our current maps of reality are merely drafts waiting for a more complete edition. The baffling data that suggests a faster-than-light planet is not a threat to science, it is an invitation. It pushes us to look closer, to question our assumptions about gravitational lensing, or perhaps even to dream of physics beyond our current horizon. What other doors might this modern mystery help us unlock? The hunt for this cosmic magnifying glass is one of astronomy's greatest challenges. You cannot simply point a telescope and see the lens itself, because the most likely culprits are the universe's very own ghost. A rogue planet drifting alone in the interstellar darkness would emit no light of its own. An isolated black hole, the ultimate gravitational pit, is by definition invisible. Even dense knots of dark matter, the mysterious substance that binds galaxies, would leave no direct trace for our cameras to capture. So how do you find something that refuses to be seen? Astronomers become detectives of distortion, searching not for the object itself, but for the subtle warps it imposes on the light of everything behind it. They meticulously analyze the starlight from the pulsar system, looking for the telltale signs of a lens at work, a slight shearing or a faint amplification that betrays an unseen mass bending the fabric of space. This is a painstaking process, like trying to spot a clear marble by the way it slightly distorts the pattern on a tablecloth beneath it. Other powerful telescopes are also enlisted, scanning the same patch of sky across different wavelengths from radio waves to X-rays, hoping to catch a faint, unexpected glimmer. Perhaps the lens is not completely dark, but a dim, failed star known as a brown dwarf, emitting just enough heat to be detected with the most sensitive instruments. The search is a monumental task, a cosmic game of hide and seek where the hider is not just invisible, but may be a form of matter we do not yet fully understand. The environment around this pulsar is a realm of pure fury. This is not a star that provides warmth and light. It is a celestial tombstone, spinning with a ferocious energy that would sterilize any world in its vicinity. The Pulsar PSR B1257+12 bombards its planets with a relentless, deadly hail of radiation, from high-energy X-rays to powerful gamma rays. Its magnetic field is trillions of times stronger than Earth's, a force capable of tearing molecules apart atom by atom. For any form of life as we know it, this system is the definition of hell. This brutal reality makes the very existence of these planets a profound puzzle. How could a world form in the aftermath of such absolute destruction? A pulsar is born from the cataclysmic death of a massive star in a supernova explosion, an event so violent it should have vaporized any pre-existing planetary system. The leading theory is that these are not survivors but phoenixes. They are second-generation planets forged from the ashes of the star's own death. When the original star exploded, it did not completely obliterate itself. A vast cloud of rich, heavy elements was flung out into space, the very debris from the stellar corpse. Over millions of years, this material could have coalesced into a new, thin disk of dust and gas circling the newborn pulsar. From this disk, a new family of planets was born, worlds built from the remains of their dead parent star. This adds a deeply poetic layer to the mystery. We are not looking at a planet that has always been, but at a cosmic revenant, a world born from a violent death, now orbiting the very engine of its own creation. Its apparent impossible speed is just the latest chapter in a life story that defies every conventional expectation. Amidst the grand theories of cosmic mirages and spacetime warps, we must also confront the humbling possibility of a simple machine error. The Kepler Space Telescope, for all its incredible precision, was a complex instrument operating in the harsh environment of space. Its digital eye was a charge-coupled device, or CCD, a sophisticated light sensor not so different from the chip in your phone's camera. And like any electronic system, it was vulnerable to glitches. A single high-energy cosmic ray, a subatomic particle screaming across the void, could have struck the sensor and created a false, pixel-bright signal that mimicked a star's momentary dimming. Alternatively, the software algorithms designed to sift through mountains of data for the subtle signs of a trance, it could have encountered a rare bug, misinterpreting noise as a signal and stitching together a phantom planet from digital static. This is the principle of Occam's razor in action, a guiding rule in science which suggests that when faced with a mystery, the simplest explanation that fits the facts is often the right one. A planet moving faster than light is an earth-shattering, universe-altering revelation. A data artifact, on the other hand, is a known, documented, and relatively common occurrence. It is far more probable that the signal was a ghost in the machine rather than a ghost in the cosmos, a reminder that our quest to understand the universe is always filtered through the imperfect, though remarkable, tools we build to see it. This mystery forces us to confront a question that lies at the very heart of science. Are the rules we have discovered here on Earth truly the same in every corner of the cosmos? For centuries, we have operated under a powerful assumption that the laws of physics are universal and unchanging. The force of gravity that makes an apple fall in England is the same force that guides the dance of galaxies a billion light-years away. The speed of light is the same constant in the heart of a distant quasar as it is in a laboratory on Earth. This principle of uniformity is the foundation upon which we have built our entire understanding of the universe. It allows us to use mathematics to predict cosmic events with stunning accuracy and to feel confident that the universe is, at its core, knowable. But what if that confidence is misplaced? The enigma of this pulsar planet, even if it is ultimately an illusion, cracks the door open to a staggering possibility. What if the cosmic rulebook is not written in permanent ink? The philosophical implications are profound. It suggests that under conditions of extreme gravity or in environments forged from stellar catastrophe, the fundamental constants we hold sacred might bend or even break. Imagine a universe where the strength of gravity subtly shifts in the void between galaxies, or where the speed of light was different in the ancient past. This is not just about one fast-moving world. It is about whether our local experience of reality is the only version that exists. The data from this single star system becomes a lens through which we examine our most basic beliefs. It asks us to consider that our laws are not universal decrees, but perhaps just local ordinances, valid in our quiet neighborhood of the cosmos, but subject to revision in the more turbulent districts. This transforms a scientific puzzle into a deeply human inquiry, challenging us to wonder if the universe is ultimately consistent, or if it allows for pockets of the truly impossible. The ultimate resolution to this cosmic puzzle may lie with a new generation of eyes on the sky. Instruments like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are not merely incremental upgrades, they represent a quantum leap in our ability to perceive the universe. Their advanced capabilities are tailor-made to dissect a mystery like our faster-than-light phantom. Imagine trying to read a street sign from a mile away with blurry binoculars and then being handed a crystal-clear telescope. That is the kind of clarity these new observatories provide. The James Webb, with its profound sensitivity to infrared light, could attempt to directly image the pulsar system itself. Seeing the planets directly, rather than inferring their existence from shadows, would instantly clarify their true orbits and eliminate a host of uncertainties. But the real power might lie in their ability to study the light with microscopic precision. Both telescopes possess instruments capable of spectroscopy, of breaking light into its constituent colors to read its story. They could analyze the starlight from the pulsar system for the subtle fingerprints of gravitational lensing, measuring the exact amount of stretching and distortion that reveals the mass and position of an intervening object. This would turn a theoretical possibility into a measurable fact. Furthermore, their unparalleled sensitivity allows them to scan the region for any faint, cool objects, like a previously unseen brown dwarf, that could be acting as the cosmic magnifying glass. If no such lens is found, the mystery deepens, forcing us to consider even more radical explanations. These missions offer the promise of a final verdict, a chance to replace tantalizing speculation with definitive data, and in doing so, either close the file on this particular anomaly or throw the entire book of physics wide open. This spirit of collective curiosity is not confined to professional labs and observatories. The search for answers to cosmic riddles like our phantom planet has ignited a global movement, one where anyone with an internet connection can join the hunt. Professional astronomers are often overwhelmed by the sheer volume of data pouring from telescopes like Kepler, data that contains countless hidden signals waiting to be noticed. This is where the power of the crowd comes in. Online platforms such as Zooniverse have revolutionized the process, turning the public from passive spectators into active collaborators. Imagine a digital workshop where millions of volunteers, from students to retirees, log on to examine real astronomical data. They might be tasked with looking at images of distant stars, searching for the subtle, repeating dips in brightness that signal a transiting planet. The human brain is exceptionally good at pattern recognition, often spotting anomalies that a computer algorithm might miss or dismiss as noise. It was through a similar crowdsourced effort that the bizarre star Boyajian star was first flagged for its erratic dimming, a mystery that captivated the world. In the case of our Pulsar planet, volunteers could help classify different types of stellar flickers or search for other, similar anomalies in vast archives of pulsar data. Every click from a volunteer is a small but vital contribution, a single pair of eyes helping to scan the cosmos for clues. This transforms the scientific process from an exclusive endeavor into a shared human adventure. You do not need a PhD to help write the next chapter in our understanding of the universe. You just need curiosity and a willingness to look. What other cosmic secrets might be hiding in plain sight, just waiting for the right person to notice them? The universe is a master of illusions, and gravitational lensing is one of its favorite tricks. This phenomenon, which offers the most elegant solution to our phantom planet, is not just a theoretical idea. We have seen its handiwork scattered across the cosmos, bending light into breathtaking shapes. One of the most stunning examples is the Einstein ring, a near-perfect circle of light hanging in the void. This occurs when a distant galaxy is positioned almost directly behind a massive foreground object, like a galaxy cluster. The cluster's immense gravity warps the fabric of space around it, acting as a colossal lens that smears the background galaxy's light into a brilliant, fiery halo. It is a perfect demonstration of Einstein's vision, where mass tells spacetime how to curve and spacetime tells light how to move. In other cases, we see a single object multiplied. A brilliant quasar, the intensely bright core of a distant galaxy, can appear as four identical copies arranged around an invisible central mass. This cosmic mirage happens when the gravity of a foreground galaxy splits the quasar's light into multiple paths, each taking a slightly different journey around the lens before all converging in our telescopes. These are not artistic interpretations, they are direct photographic evidence that gravity can twist and magnify light on a cosmic scale. The same fundamental physics that creates these beautiful rings and multiple images could also be stretching the apparent motion of a distant planet, making a fast orbit look impossibly fast. Our universe is not a static picture. It is a dynamic hall of mirrors where every observation is filtered through the invisible lens of gravity. What we see is not always what is truly there, but a reflection shaped by the mass hidden in between. The most challenging aspect of this work is that we are not just looking at a planet, we are looking at a planet through a funhouse mirror. My team spends countless hours trying to model that mirror. Imagine you hear an echo in a vast, complex cave. You can measure the echo perfectly, but without knowing the exact shape of every wall and stalactite, you can never be sure where the original sound came from or how fast it was truly moving. That is gravitational lensing. We have the echo, the distorted data, and we are trying to reverse engineer the shape of the invisible cave. The excitement for me comes from that very uncertainty. When the data first came in, my initial reaction was not that we had broken physics, but that we had found a spectacular puzzle. It is in these moments, at the very edge of our understanding, that we have the chance to learn something truly new. Personally, I find the lensing explanation the most compelling. It fits within our known physics, yet it requires a cosmic coincidence so perfect it feels special. The universe is showing us one of its most dramatic magic tricks. To see that trick and to finally understand the mechanism behind it, that is a profound discovery. It reminds us that reality is often stranger than the illusions we mistake for it. The allure of a planet shattering the light barrier inevitably sparks wild speculation, but we must carefully separate cinematic fantasy from scientific fact. This anomaly is not evidence of an alien superstructure harnessing the pulsar's energy. Such a civilization, if it existed, would have no need to violate physics to move a planet when simpler, slower methods would suffice. The idea of a natural wormhole, a tunnel through space-time, bending the planet's path is equally unsupported. Wormholes are theoretical constructs that would require exotic matter to remain stable, a substance we have never observed, and their spontaneous appearance to consistently affect a single planet's orbit stretches credibility beyond its limit. This is also not a crack in the universe's fundamental code, a place where the rules simply stop working. The cosmos is consistent. If the laws of physics were truly broken here, we would see the repercussions everywhere, a universal unraveling that we simply do not observe. The real explanation, while less sensational, is far more profound. It relies on the known, tested laws of gravity and light, a cosmic illusion created by the universe's own inherent properties. This distinction is crucial. Embracing the fantastical might be more exciting, but it closes the door on genuine discovery. The disciplined path of critical thinking, of questioning even the most thrilling possibilities, is what truly allows us to peer deeper into the cosmos's real wonders. The universe is strange enough without inventing new physics. Our task is to understand the magnificent rules that already exist. Deep down, this cosmic phantom speaks to something ancient within us, a yearning to find a crack in the universe's walls. We are a species born of explorers, our history written by those who pushed against the edges of the map. For centuries, those edges were geographical, the blank spaces marked here be dragons. Today, the last great terra incognita is the cosmos itself, and its ultimate boundary is the speed of light. This law is the final no trespassing sign on the interstellar highway. So when data hints that a world might be ignoring that sign, it does more than puzzle scientists. It ignites a primal spark of hope and wonder in all of us. It whispers that the universe might not be as rigid as our equations suggest, that there could be backdoors and secret passages hidden within the laws of physics. This is not just about one anomalous planet. It is a symbol, a celestial stand-in for our deepest aspirations to roam the stars. Every science fiction story about warp drives and hyperspace jumps has prepared us for this moment, making the impossible feel tantalizingly within reach. The mystery endures because it offers a thrilling possibility that the greatest adventures are not over, and that the cosmos still has miracles in reserve, waiting just beyond the glow of our understanding. This phantom world joins a cosmic menagerie of the strange and the extreme. To understand its place, we must hold it up against the other oddities we have found in the dark. While its speed may be an illusion, its environment is a confirmed hellscape, rivaling the most brutal conditions imaginable. Take the lava worlds, planets like Kepler 10b, locked in a gravitational embrace so tight with their star that their surfaces are vast, global oceans of molten rock, where the very ground is liquid fire and the skies rain vaporized stone. Our Pulsar planet endures a different, more invisible torment, a constant bath of radiation that would instantly strip a lava world to its atomic core. Then there are the diamond planets like the famous 55 Cancri, a world thought to be composed largely of crystallized carbon, a glittering jewel the size of Earth. These form under immense pressure, transforming common elements into cosmic treasure. The world around PSR B1257+12 is forged from a different kind of pressure, born not in the heart of a stable star but in the radioactive debris of a stellar corpse, making it less a jewel and more a monument to destruction. And what of the rogue planets, those lonely nomads cast out from their solar systems to drift forever in the frigid darkness between stars? They are the ultimate orphans of the galaxy. Our mysterious object, by contrast, is bound in the most violent of relationships, chained to a star that constantly tries to annihilate it. Each of these discoveries pushes the definition of a planet. One is a world of fire, another of ice, another of priceless crystal. Our subject is a world of pure energy, a testament to the universe's boundless creativity in constructing nightmares. Its apparent speed sets it apart, but its very existence places it firmly within a growing catalogue of cosmic aberrations, proving that nature's imagination far exceeds our own. The story of this cosmic mystery began with a single particle of light, a photon that had traveled for thousands of years. It ended its journey by striking a precise, silent sensor aboard the Kepler Space Telescope, a tiny pixel among millions flickering to life in the deep cold of space. This faint electronic whisper was not yet data, just one point in a vast sea of noise. But as more photons arrived, tracing the steady brightness of the pulsar, a pattern began to form. A computer algorithm trained to hunt for the telltale dips of transiting planets flagged a subtle, repeating change. It was an automated process, a relentless sifting of numbers that transformed starlight into a simple, powerful graph. A line on that graph dipped downward, a signature of something passing in front of the star. This digital alert landed in the inbox of an astronomer who saw not just a dip but a puzzle. The numbers describing the dip's duration and frequency were fed into the established equations of orbital mechanics. The result was a velocity that made no sense, a number that should not exist. This single data point, born from a photon and amplified by code, now became an anomaly. The astronomers' findings were then wrapped in the cautious, precise language of science, submitted to a journal and scrutinized by anonymous peers. The published paper was a careful document filled with uncertainties and alternative explanations. But when the press release was drafted, the most cautious phrases were often the first to be trimmed. The headline that reached the world was stripped of its nuance, transforming a complex maybe into a sensational impossible. A single point of light, transformed by machines and minds, had become a global story, proving that every great cosmic mystery is built upon a fragile chain of interpretation. So let us play with an idea, a thought experiment that pushes beyond the lensing illusion. Suppose, just for a moment, that this planet truly was moving faster than light. What impossible spectacle would we witness from our distant vantage point? The first casualty would be our sense of time. Because light has a finite speed, we always see celestial objects as they were in the past. We see the Sun as it was 8 minutes ago and the Andromeda Galaxy as it was 2.5 million years ago. But a faster-than-light object would break this chain. It would, in essence, outrun its own light. Imagine the planet at point A, emitting light that travels toward us. The planet itself, moving faster than that light, arrives at point B before the light from point A does. From our perspective, we would see the planet appear at point B first. Then, moments later, we would see the older light arrive, showing the planet back at its original position, point A. We would witness the effect before the cause, seeing the planet in two places at once, its past and its present unfolding in a jumbled, impossible sequence. This is more than a visual trick. It is a violation of causality, the fundamental principle that cause must always come before effect. Such a planet would not just be moving through space, it would be unraveling the timeline itself, creating a universe where a traveler could theoretically arrive back home before they ever left. While this is almost certainly not happening around Pulsar B1257+12, the mental exercise reveals why the light-speed barrier is so essential. It is not merely a rule about velocity, it is the guardian of logic, the thread that keeps the tapestry of reality from fraying into chaos. The phantom planet story is a perfect echo of science itself, a journey that values the question more than a quick answer. While the breathtaking possibility of a world moving faster than light was almost certainly an illusion, a cosmic sleight of hand performed by gravity, its true legacy is not a disappointment but a triumph. This single anomaly, this stubborn piece of data that refused to fit, forced a rigorous and beautiful process into motion. It compelled scientists to question their most basic assumptions, to double-check their math, and to explore the furthest reaches of known physics for an explanation. That process of collective scrutiny, of building and testing simulations, is the engine of human understanding. it is how we turn bewilderment into knowledge. Every great leap forward, from Newton's gravity to Einstein's relativity, began exactly like this, with an observation that did not make sense. So the next time you find yourself under a clear night sky, look up at those countless points of light. Remember that each one is not just a star, but a potential story, a mystery waiting for its chapter to be written. The greatest discoveries are still out there, hidden in the dark, and they will only reveal themselves to those who are brave enough to ask what if. What do you think is the next great cosmic mystery we will solve? Share your thoughts below.